Imagine this, thousands of galaxies, each with billions of stars, are all moving in the same direction. But why? Welcome to the enigma of dark flow. In the vast expanse of space, an unexplained phenomenon is taking place. It's like an invisible current in the cosmic ocean, guiding galaxies towards a particular point. We call this phenomenon dark flow. Now, dark flow isn't your everyday mystery. It's a cosmic conundrum that has left scientists scratching their heads for years. Picture this: a colossal collection of galaxies, each one a bustling metropolis of stars, planets, and cosmic dust, all moving in unison towards a specific direction. It's like they're all being summoned by an unseen force, an intergalactic Pied Piper, if you will. But what could possibly wield such gravitational influence to set galaxies in motion? Dark flow isn't just a curiosity. It's a fundamental aspect of our universe that we're yet to fully understand. It challenges our current understanding of the universe's structure and origin. It's a testament to the vastness and complexity of the cosmos. To give it a bit of context, our observable universe, the part of the cosmos we can see and study, is about 93 billion light-years in diameter. Now, dark flow suggests the existence of cosmic structures even beyond this observable universe, structures so huge that they can pull galaxies towards them. Mind-boggling, isn't it? The theories about dark flow are as numerous as the stars in the sky, each one more intriguing than the last. Some propose the pull of distant superclusters, others point to the influence of cosmic strings or dark energy. There are theories about quantum fluctuations, the presence of another universe, and even the possibility of structures beyond what we can observe. Are you intrigued yet? Let's dive into the top 10 theories that attempt to unravel this mystery. Theory number 10 suggests the pull of distant superclusters as a possible explanation. Now, what are superclusters? Think of them as colossal cosmic communities, massive groups of galaxies bound together by gravity. In the grand scheme of the universe, they are the largest known structures, dwarfing our own Milky Way galaxy. It's proposed that these distant superclusters might be exerting a gravitational force strong enough to cause the observed dark flow. Imagine a cosmic tug-of-war, these superclusters pulling entire galaxy clusters towards them. It's a fascinating thought, isn't it? However, like any good mystery, the plot thickens. The gravitational pull of these distant superclusters, while substantial, might not be enough to account for the velocity at which these galaxy clusters are moving. The math just doesn't quite add up. Although plausible, this theory falls short in fully explaining the phenomenon. But don't lose heart, we have 9 more theories to explore. Stay tuned. Next up, Theory 9 points towards the influence of cosmic strings. Now, what are cosmic strings, you ask? Well, they're hypothetical, one-dimensional topological defects in the very fabric of the universe. Think of them as invisible stitches holding the universe together. In this rather intriguing theory, cosmic strings could be causing dark flow. These strings are believed to be incredibly dense, with a mass per unit length that could be astronomical. As a result, they could exert a significant gravitational pull on galaxy clusters, causing them to move in a unified direction, the phenomenon we refer to as dark flow. But, just as the strings themselves, this theory is also largely hypothetical. The existence of cosmic strings has not been proven, and neither has their influence on dark flow. As with many aspects of our vast universe, there's so much more to explore and understand. As fascinating as this theory is, it remains largely speculative. At number 8, we have the role of dark energy. This enigmatic force is thought to permeate all of space, accelerating the expansion of the universe. Some theorists propose that dark energy could be the driver behind the mysterious dark flow. Imagine dark energy as an unseen wind, ever present and pushing galaxies in a particular direction. This force could be responsible for the observed movement of galaxy clusters, nudging them towards a specific point in the cosmos. However, the role of dark energy in dark flow isn't a slam dunk. There's a significant challenge to this theory. Dark energy, by its very nature, should affect all parts of the universe equally. So why would it cause a flow in one particular direction? While dark energy is a widely accepted component of our universe and a crucial part of our understanding of cosmology, its connection to dark flow remains a topic of heated debate among scientists. While dark energy is widely accepted, its connection to dark flow is still uncertain. Theory 7 introduces the impact of quantum fluctuations. Now, you might be asking, what are quantum fluctuations? Well, they're temporary changes in the amount of energy in a point in space as allowed by the Heisenberg uncertainty principle. But how does it tie to the dark flow? Imagine the early universe as a quiet ocean. Suddenly, a tiny ripple, a quantum fluctuation emerges. This ripple then gets amplified by the rapid expansion of the universe, known as cosmic inflation. Now, this is not just any ripple. It's a ripple in the fabric of space-time itself, which can create areas of slightly higher or lower density in the universe. The theory suggests that these fluctuations could have caused variations in gravitational forces which eventually led to the dark flow. It's like a cosmic tug-of-war, with galaxies being the rope. Intriguing as it is, this theory lacks concrete evidence. Number 6 suggests a pre-Big Bang scenario. Now let's venture into an intriguing concept that challenges our understanding of time's origin. The theory proposes that dark flow might be a relic from a time before the Big Bang. We're talking about a period that seemingly defies the laws of physics as we know them. Imagine, if you will, a universe existing before our own. The imprint of its cosmic movements and force fields could have been carried over into the universe we inhabit today, resulting in the unusual unidirectional flow of galaxy clusters we call dark flow. If true, this theory would provide a radical new perspective on the universe's origins and evolution. It dares to contemplate the seemingly unanswerable question: what existed before the Big Bang? Was there another universe? Another reality that preceded ours? This theory tantalizes us with the possibility of understanding what came before the Big Bang. It's a thought that stretches the mind and challenges the boundaries of our cosmic perception. Halfway through, at number 5, we have the presence of another universe. This intriguing theory delves into the concept of multiverse, a hypothetical group of multiple universes, including the universe in which we live. Imagine for a moment, our universe is but one bubble floating in a sea of other bubbles, each unique in its own existence. Now consider that the gravitational pull of an adjacent universe might be strong enough to cause the observed dark flow. Our galaxies, like cosmic driftwood, could be getting swept along a universal current, pulled by the gravitational forces of a neighboring universe. Whilst this theory is tantalizing, it's important to note that it's purely speculative at this stage. The existence of other universes is yet to be proven, but if it holds true, this theory could provide a plausible explanation for the enigma that is dark flow. This theory opens up a whole new realm of possibilities and questions. At number 4, we have the void hypothesis. This one really flips the script by suggesting that the observed dark flow is not caused by something pulling the galaxy clusters, but rather something is pushing them. Imagine a large, low-density void in our universe. Due to its low gravitational pull, it could effectively push galaxy clusters away from it, resulting in the movement we observe as dark flow. This hypothesis is fascinating for a multitude of reasons. Not only does it challenge our understanding of how gravity works on a cosmic scale, but it also raises questions about the very structure of our universe. Is it possible that there are vast, empty voids lurking in the depths of our cosmos? The void hypothesis dares to suggest so. In a realm where seeing is believing often holds true, the void hypothesis reminds us that sometimes it's what we can't see that holds the answers. This theory challenges our understanding of the universe's structure. Third in line is the influence of a non-trivial topology. This theory proposes that the universe's shape and structure could be responsible for the dark flow. Picture this: the universe as a complex multi-dimensional shape, twisted and folded in ways that our three-dimensional minds struggle to comprehend. This intricate structure or topology might be causing galaxy clusters to move in a specific direction, creating the phenomenon we call dark flow. It's as if the shape of the universe is guiding these galaxies like a river channel guides water. The galaxies are not merely moving randomly, but following the curves and folds of the universe itself. But here's the catch. This theory is highly dependent on advanced mathematics and concepts that are far from being universally accepted. It's a beautiful idea, mathematically speaking, but it's not without its critics. Some argue that it's too speculative, and that we need more empirical evidence to support it. While this theory is mathematically appealing, it's still a topic of debate. Almost there. At number 2, we have the Great Attractor. Now, this isn't your average celestial object. The Great Attractor is a gravitational anomaly in intergalactic space that is pulling galaxies towards it. Yes, you heard that right. Entire galaxies are being drawn towards this mysterious entity. This theory suggests that the Great Attractor is a colossal unknown object, or perhaps even a collection of objects, that's so massive it's warping the space-time around it. This warping creates a gravitational pull so strong that even galaxies millions of light years away can't resist its allure. But what is it exactly? A supermassive black hole? A colossal galaxy cluster? Or perhaps something entirely unknown to us? The truth is, we don't know. The Great Attractor lies in a zone of the sky known as the zone of avoidance that's obscured by our own Milky Way galaxy. This theory is exciting, but it lacks definitive proofs. And finally, at number 1, we have structures beyond the observable universe. This theory, in its fascinating and audacious nature, suggests that the observable universe is not all there is. Our universe, the one we can detect and measure, may just be a tiny bubble within a vastly larger cosmos. This larger cosmos could contain structures of such immense scale that we cannot even begin to fathom their size or nature. It is proposed that these structures, existing beyond the edge of our observable universe, exert a gravitational pull that influences the movement of galaxy clusters, resulting in the phenomenon we call dark flow. This concept challenges our understanding of the universe as it calls into question the widely accepted cosmological principle that, on large scales, the universe is homogeneous and isotropic. Imagine, if you will, colossal structures, unseen, unfelt, yet powerful enough to tug at entire clusters of galaxies, pulling them towards an unknown destination. This is the kind of scale we're talking about when we refer to structures beyond the observable universe. The thought is as humbling as it is mind-boggling. But how can we prove the existence of such structures? Currently, we cannot. Our technology, as advanced as it is, has its limits. The edge of the observable universe is the furthest we can see, limited by the speed of light and the age of the universe. Anything beyond that remains shrouded in mystery, inaccessible and unobservable. Yet the observable effects of dark flow suggest that something out there is influencing the cosmos within our sight. This theory, compelling as it is not without its critics. There are those who argue that dark flow could be explained by variations in dark energy or by a universe that isn't as homogeneous as we think. Yet the idea of structures beyond the observable universe continues to hold sway due to its potential to explain this cosmic conundrum. While this theory is currently the most accepted, the true explanation for dark flow remains a mystery, reminding us of the vast, unexplored cosmos that awaits our discovery. Before we wrap up this cosmic journey, we'd like to take a moment to thank you for joining us. If you've learned something new from this video, then please give a like to show your support. Do you have any theories about the mysteries of dark flow and the structures beyond the observable universe? Or perhaps you have questions, ideas, or other thoughts on the vast cosmos that we've explored together today. We'd love to hear your opinions, so please share them in the comments below. And don't stop there. This universe is a shared experience, so why not bring your friends and family into the conversation? Share this video with them, and let's get more people pondering the mysteries of the cosmos. Lastly, if you haven't already, don't forget to subscribe and press the bell icon. That way, you'll be notified whenever we release more content like this. The cosmos is vast and filled with mysteries yet to be uncovered. Together, let's continue to explore, question, and marvel at the wonders of the universe. Remember, the universe isn't just out there, it's also within us, in our curiosity and quest for knowledge. So stay curious, stay open-minded, and as always, keep looking up. Until next time, this is your Cosmic Journey signing off.